So welcome back, everyone. It is my pleasure now to introduce Jonathan Pila. Jonathan Pila is professor at the University of Oxford. He's an expert in number theory and model theory. In particular, of course, being the architect of the recent proof of the Andr conjecture. So he obtained many prizes, including the Clay Research Award, the LMS Prize, Fellow Royal Society, and very recently the 2022 Shock Prize. So congratulations for this. He got his PhD in 1988 under the direction of Peter Sarnak. And he worked previously in Stanford, Columbia, McGill, Bristol, also a visiting member of the IES. So please, Jonathan Pila.
Yeah, thank you. Thank you very much.
So you will talk about
atypical
point counting on the Andr conjecture.
Yeah, thank you very much. Yeah, so it's a great honor and pleasure to be here at the Symposium in honor of Enrico, who's made so many great contributions, well, all over our subject and beyond number theory. And I'm personally, it's an extra pleasure because of the importance of our own collaboration in my work. So this talk will have two connections with Enrico's work. First, I want to describe a line of problems, Diophantine problems, which Enrico pioneered with David Massa and Umberto Zagna, and which led them and others to formulate a very general conjecture. That's the atypical, the conjecture on atypical or unlikely intersections. And then I want to describe a little bit about the work that began in my collaboration with Enrico and which eventually developed into a tool which has been quite useful in tackling some of those problems. And I guess, yeah, so because of that dual nature, I won't be probably talking in very much detail about the Andr conjecture, but I want to say a bit about the strategy. So that's my plan. So I want to begin with this line of Diophantine problems, and some Diophantine problems. Oh. All right, and I want to begin with the very simplest example of this kind of problem. So this is Lang's problem. So this is the simplest example, is this problem of Lang's problem. Although, as we'll see, it was in some sense a toy problem. Even when he brought it up, there were already much more sophisticated problems around. And he, in a period, well, anyhow, I'll say a little bit more about it, but it's sort of not the first problem, but it was a kind of a backwards constructed simplest case of this kind of problem. So we're going to consider a curve, V. I'll call my curve V, and it'll sit, we're going to consider this curve sitting in C cross squared, the non-zero complex numbers, which is, well, and this curve, let's say, we can think about it quite concretely as being defined by some polynomial f of x, y equals 0. And the problem is to try to solve f of xy equals 0 in roots of unity. That was the problem. And the roots of unity, of course, are just the torsion points of C star squared. C star is a multiplicative group just under component-wise complex multiplication of complex numbers. And so the theorem, so the question was, when can there be infinitely many solutions to this problem? And the theorem, for which in the paper in about 1960, I think Lang presents proofs due to Ihara, Sayre, and Tate. So he must have discussed this problem around a bit, and he got a couple of solutions. That there are only finitely many So here, to solve, so in roots of unity, by that I mean a pair zeta, eta, let's say, for which fxy equals 0, and those are roots of unity. That there are only finitely many solutions unless one is in the obvious situation where there are infinitely many solutions, and that is that f is of the multiplicative form. Specifically, that f is some constant times x to the n, y to the m, minus some root of unity, where here n and m can be integers. So I've cheated a bit. I mean, this might not be a polynomial, right? But rather than having two different special forms, so we'll allow nm in integers, not both 0 and zeta as a root of unity. And in that case, this V is, well, it's not quite a subgroup, it's a coset of a subgroup. By torsion point, it's what we call a torsion coset. All right, so a slightly harder problem of this kind is to solve the same equation for x and y in some finitely generated group. Say 2 to the z, whoops, 3 to the z, 5 to the z. Just for example. So this is a later theorem of Liade. So in fact, you can even try and solve it in the division group of a finitely generated group. And again, the theorem is that there are only finitely many solutions unless f or v, I should say, v is, or f is of this special multiplicative form, which corresponds to v being a coset. Well, sorry, I'm being a bit too quick. Well, no, let's say a coset by a div gamma point of a subgroup. And both of these then special cases of, let's see if I can fit this theorem here. What we could call the multiplicative Mordell-Lang theorem of Michel-Laurent. And that's where you generalize all of this to a subvariety of C star to the n. And you go about trying to solve well, either this problem or this more general problem, torsion points, or points in the division group of a finitely generated group, which says that if you intersect V with this division group is contained in the union of finitely many div gamma cosets, let's call them T, which are contained in V. So this is really somehow the best result you could hope for, because, I mean, here you can actually hope for finiteness in the non-exceptional case, but in general, your variety V might actually contain groups, actual subgroups of lower dimension. And so somehow this is the right statement. This is the best statement you can get in this situation, that there are finitely many things like these exceptional things that are contained in V and that account for everything. All right, so these problems are the multiplicative analogues. You see here we're talking about the multiplicative group, gm squared, or here gm to the n. So these are the multiplicative analogues of a more famous line of problems, starting with the Mordell conjecture of 1922, which was proved by Faltings in 1983. And I don't want to, I'll say a little bit of this, but I don't want to write it all down. So Mordell's conjecture, which I guess was the major conjecture in Diophantine geometry for a big chunk of the 20th century, that on a smooth projective curve, V, let's say defined over Q, and of genus at least 2, you have only finitely many rational points. Okay, so on the elliptic curve, as Mark just showed us in his talk, you have a finitely generated group. And in the same paper where Mordell proved that statement for the finite generation of the rational points of an elliptic curve over Q, he makes a series of conjectures at the end of the paper. And the last one was that if the genus is at least 2, then there are only finitely many rational points. And that was proved finally by Faltings in 1983. But somehow in the meantime, you see a curve can be embedded in its Jacobian, which is an abelian variety, as we've just heard about. And the abelian variety, the rational points there are finitely generated by the theorem of Mordell and Weil. And so you are then looking at this kind of problem, intersect a curve with a finitely generated group. And Lang was kind of reverse engineering this to consider the multiplicative group into the picture. Of course, the multiplicative group, the rational points on the multiplicative group are not finitely generated. That's by a famous theorem of Euclid, that there are infinitely many prime numbers. And he was also, of course, here also incorporating, thinking about the Mann-Mumford conjecture, where you look at torsion points in the same embedding. So this was all part of a picture of, and he went on to formulate the Mordell-Lang conjecture, and which was then somehow proved in a series of works, starting with the Faltings theorem, and with a series of work with, well, including Laurent and Raynaud on the Mann-Mumford, and Hindry and Voita, and that list of people usually ends with McQuillan, who proved the semi-abelian Mordell-Lang. All right. So this is some Diophantine problems, and we've got the multiplicative ones, and we've somehow talked a little bit about the bigger picture. And the next thing I want to talk about are the unlikely, or atypical intersections. All right, so we've heard about BV and we've heard about BFI in James' talk. So in my part of the world, we talk about BMZ, Bombieri, Massa, and Zanya. And in a line of papers, they were led to consider some more general problems, led to consider some more general problems. So I'm going to take my curve. I like this as an example, sort of modeled after theirs, and I like it. But I'm going to consider a curve that's a parameterized curve. So let's consider the curve, the set of points t1 minus t, 1 plus t squared. And then I'll have 2, 3, 5, so there'll be some fixed coordinates of the points on my curve. And I'm going to consider this for t to be a complex number. And I want to consider this curve to be in C cross to the 6th. And so I'll have to leave out a few t's where these numbers are, where these things become 0. I'm just leaving a few points off my curve. And you can consider any, or you could put any curve here, or any curve V0 in C cross cubed, say. But I just to think concretely. And now we want to consider, so this is a curve now in a 6-dimensional space. So if you intersect it with a 4-dimensional subvariety, then in general you would expect these things not to intersect. But of course, they might, and that's what we will call an unlikely intersection. And we're going to consider it when you intersect with 4-dimensional subgroups. So we're going to and a 4-dimensional subgroup is formed by imposing 2 multiplicative conditions. So let's consider, consider subgroups defined by 2 or more, but let's say 2 multiplicative relations. In other words, we're just going to impose 2 relations like this, x to the 6th, right. So what might these relations say and what could happen? Well, those 2 relations might just say, let's say that t and 1 plus t squared are roots of unity. And then you'll be looking at this problem on the projection of this curve onto those coordinates. Or these 2 relations might say that these 2 are in the division group of 2, 3, and 5. And then you'll be looking at the projection at this problem on the projection on those 2 coordinates. But in general, if you just impose 2 conditions like this, they won't be of either of those special forms, and they will just say that there are 2 multiplicative relations on the points of the curve. And that was the kind of problem they were led to. So let me write the theorem. So it was BMZ in some initial cases, I think up to, I forget exactly what ambient dimension and so on. And the general case is due to Morin. That a curve V contained in X, which is GM to the N, not contained in any proper subgroup. So let V be a curve not contained in any proper subgroup. Then the intersection of V with what I'll call X2 is a finite set. And here this X2 is the union of subgroups of codimension at least 2. So let me put that now up there and this down. So I want to write this X because there'll be a more general conjecture. So the form of this conjecture is that this X is an ambient variety of some special form. Here it's a multiplicative group, and we consider subvarieties, and we intersect V with this collection of particular, or what one calls special subvarieties. So if X is a group, then the special subvarieties are the subgroups. And we'll see later that the Andr conjecture takes exactly this kind of form. And the point of the theorem, of course, is that this X2, this is a countably infinite union. This is right. So there are somehow infinitely, sort of a countable number of possibilities for this intersection to take place, and yet only finitely many do. That's the content of this conjecture, as it was here, that of this countably infinitely many torsion points, only finitely many can land on V, unless you're in the special case. Right. So, right. So now I can state the more general form of this problem. Right? Yes. Well, okay, thanks. I've got this one. Now that I've got this one prepped, I think I better... Right. So part 3 is something called the Zilber-Pink conjecture. So this is somehow a higher dimensional version of that conjecture, and then a sort of still more general version. And it was framed independently by Zilber and by BMZ, and then in the most general form by Pink. So, all right, so what's the general form? So we're going to consider an ambient variety X, which you can think of as being GM to the N, or an abelian variety, or later it will be something more general. It'll be a Shimura or mixed Shimura variety. And this X sort of comes with a collection, which I like to call curly S, of special subvarieties. So the special subvarieties are somehow things with a similar geometry. They're subvarieties of X with somehow a similar geometry. So in the case that X is a multiplicative group, these are cosets of multiplicative subgroups. And in the case, cosets by torsion points. But in general, you should think of them as somehow an infinite, countably infinite collection of subvarieties of X that have somehow a similar geometry. And V is a subset of X. And now we look at subvarieties of V. So let A be a subvariety of V, and we'll call it atypical if on the one hand, A is a irreducible component of the intersection of V and T for some special subvariety T. And if this component is atypical in dimension, so that means that the dimension of A is bigger than what you'd expect, and what you'd expect will be the dimension of V plus the dimension of T minus the dimension of X. That's if everybody intersected, normally. And then we let the atypical set of V be the union of all atypical subvarieties. And the conjecture is that the atypical set of V is a finite union. So again, these special subvarieties are always a countably infinite collection, so you've got countably infinitely many possibilities for these components. And the conjecture is, well, not that there are only finitely many of them, because there might be infinitely many, but that somehow when you add them all up, that they're accounted for by finitely many. So in the case of a curve, this is exactly this statement, in fact. Because where you have a curve, the only possible atypical components, the only subvarieties of a curve are either points or the curve itself. The curve itself will be atypical if it's contained in a proper subgroup, which is the case I excluded in the hypothesis. And otherwise, the atypical things are only points. And then the theorem is there are only finitely many. So this here confirms the Zilberpink conjecture for a curve in a multiplicative group. Now, I should say also that I've written there unlikely intersections and here atypical subvarieties, and there's a mixture of terminology. This conjecture was somehow arrived at by different people, and some people called these things atypical, and some people called them unlikely. And unlikely, in fact, well, more technically, is when you would expect no intersection at all on account of the codimensions, whereas atypical is simply when the component is too big in dimension. Now, so if X is a multiplicative group, then this conjecture implies the full Mordell-Lang. If X is an abelian variety, and you take the collection of special subvarieties to be torsion cosets of abelian subvarieties, you again get a conjecture which implies the full Mordell-Lang. And this was Pink's realization that if you now allow X to be a Shimura variety, or a mixed Shimura variety, then you would also include the Andr-Oort conjecture, but also a whole lot of other statements that go far beyond it, analogues of this kind of statement. And I guess the other point to make here is that this conjecture is very, very wide open. So Morin's theorem proves it for a curve, and it's open for, in general, for V of dimension 2. Although there are, all right. So now I want to talk about point counting. So the Andr-Oort conjecture now somehow sits in this sort of very big conjectural picture. So, all right, so this is for point counting. So this goes back to this collaboration of mine with Enrico, and we wrote a paper which proved various results to the effect that if you take a plane curve, just curve in the xy plane, then it has rather few integer points on it, unless there are various kind of, unless there are reasons somehow. And the same kind of approach gives the following theorem. So let's consider z in R squared be the graph of some function f from 0, 1 to R. And let's say this f is a real analytic function on a neighborhood of 0, 1. And it's not an algebraic function. And epsilon is some positive constant. Then you can prove that there are rather few rational points on this graph. Now, you have to somehow be a little bit careful how you formulate the few rational points, because there are examples that go back to Weierstrass where this f can take a rational value at every rational point. So in some sense, it's taking rational points absolutely everywhere. They're totally dense. But if you count them by the height, then they have to become rather sparse. So here I'm going to look at the xy's in z intersect q squared, such that h of x and y is at most t. And here, h of p over q in lowest terms is simply the max of mod p and absolute value of p and q. In Mark's talk, we had this height too, I think, but we also had the logarithmic version of it. This is the absolute multiplicative height. It's just the maximum of p and q when they're in lowest terms. And in that case, the number, if you count the points up to height t, you get at most some constant depending on f and epsilon, t to the epsilon for every positive epsilon. So that's saying that there are few rational points, that somehow the heights have to increase rather quickly. Now, this, if you look for generalizations of this theorem, so let's look to generalize it. So generalization to set z in R to the n. All right, and I'm going to say a little bit, but so we're going to have to put some conditions on this set z. You can't hope to prove estimates of rational points on arbitrary sets. So we're going to take this set z to be definable in an O-minimal structure. And I'm going to say a little bit about that in a minute. So we'll just take that to be, we'll just take that to be a bit of an undefined term, but we'll note that it includes a higher dimensional analog of this, which is the image of some m-dimensional box in R to the n, which is real analytic on a neighborhood, say. It includes that kind of set. It includes, crucially, some broader sets. And then we have, for this kind of set, something I'll call the counting theorem, which I proved with Alex Wilkie. So Z is a definable set. Let Z be definable in an O-minimal structure, and epsilon greater than 0. Then, if you do the same count, well, I need to leave myself some space. So let me stop there for the moment. Can people still see this, or is that going to be anyhow? Well, so we want to count the points in Z which are rational points of height at most t. And now we have an issue that here it was, if this f is non-algebraic, we get a good estimate. But here this is a higher dimensional set, and it might, for example, contain lines or planes, or it might contain algebraic sets that actually do contain a lot of rational points. And so what we do is we exclude them. Oh. So what we're going to do is, well, so here I'll write Z in Q to the N. And here I'm going to exclude what we call the algebraic part. And the algebraic part is the union of all positive dimensional connected semi-algebraic sets which are contained in your set Z. So these are sets where you might have a lot of points. Let's say, I mean, keep in mind, say, a following example, that your set Z might be the graph of little z equals x to the y. This is a highly transcendental set, but whenever y is a rational number, you've got an algebraic curve in there. And then the answer is, if you exclude all the positive dimensional things, then you get at most a constant, depending on z and epsilon, t to the epsilon, just as you have here. And not only that, you can actually, instead of just looking for rational points, you can look for points where each coordinate, let's say, is of some fixed degree. So here you can take d to be some positive integer, whoops. And then there's a d here. Then your constant also depends on d. All right. Right. So now I want to say a little bit about this, what it means to be definable in an O-minimal structure. So I think that's an important concept here. So this would be, well, so let's say just a little bit about what is an O-minimal structure. So this is a notion from model theory. And the idea in model theory is that you study mathematical structures in a fixed language. So you somehow fix at the outset what things you're allowed to talk about. And then you somehow can prove things about what you can say in that language or with that amount of structure. So here the O-minimal structure, so typically your structure consists of some set, which in this case would be the real numbers. It's customary to then use some kind of slightly different symbol for the structure R. So in O-minimal structures, you've got some set, which is usually the real numbers, which is totally ordered. So you usually just take the ordinary ordering, and then has some other structure on it, which you usually take to include the field structure, and then some other things. And then a definable set is simply a set in some Cartesian power of the basic structure, which has a definition in this language, in using symbols of first-order logic. So the typical thing might be, you could say, well, let me say one thing that you might want to add here is the exponential function as a new function on your set. And then you could say things that, like that you want p of z1 to p of z e to the zn equals 0 for some polynomial, but you might also want that q of the same thing is not 0, and you might also want some various algebraic conditions on the xi's, or you might want that for all x3 something else is true but not something else. This is typical first order sort of condition. The other way of giving this definition is that the definable, that an O-minimal structure is simply a collection for each n of some designated sets. So this Sn is a subset of the power set of R to the n, such that each Sn is a Boolean algebra, because you're allowed to use not in this language here, and or, and is so each Sn is a Boolean algebra. It's the whole collection is closed under projections. It contains semi-algebraic sets, because here we're assuming you've got these things. And then there's the O-minimal condition. So far I've just defined a structure. And the first order definable sets in any model theoretic structure will be a structure in this sense. And the O-minimal condition is that the definable subsets of R itself are just finite unions of points and intervals, possibly unbounded intervals. And the idea is that so that the definable subsets of R itself are as few as they could be, given that you have this. This is the O-minimal, the order minimal, that in R itself you can only define what you can define with the order and arbitrary real parameters. I should have said we allow these P and Q to have arbitrary real coefficients in our definition. So that's a slightly odd condition, but it turns out to be very powerful. You see, in R squared, you will typically have all kinds of other sets, but the fact that whatever you do, you can never get more than that kind of set in the base is very powerful. So for example, a function like sine x can never be definable in an O-minimal structure. Let's say the graph of sine x.
You're allowed to throw in exponential functions. So
yes.
But you would not be able to throw in sine x?
That's right.
So what, can you give us some feel for what analytic functions you would possibly?
Yeah, no, yeah. Well, so this is just a definition. So a lot of the work in O-minimality is actually showing that certain functions can be put in. So let me just say something first, that somehow O-minimality is often somehow presented as a fulfillment of a Grothendieck's idea of a tame topology. Grothendieck says somewhere that somehow topology has been invented by analysts for their own purposes and is full of space-filling curves and nowhere differentiable functions, and we need a tame topology. And actually at a rather similar time, Van den Dries was considering just this kind of condition, but with the specific idea, if you like, of trying to say something about this function. Now, if you consider univariate functions built up from exp and log and algebraic functions, then it goes back to Hardy that you get a Hardy field. These functions can never overtake each other infinitely often at infinity, which this one would. But this is somehow a much stronger condition because you're allowed to do things in arbitrary dimensions and also project and take complements and then do other things. So so this function you can never put in an O-minimal structure, although you can put pieces of it, because you can have this together with all these collections of f from an arbitrary bounded box in m dimensions, real analytic on a neighborhood. This structure here is called Rn(x). The O-minimality here was proved by Wilkie. That was somehow the major theorem, was to actually prove that that has this property. That represents some strong finiteness statement. And then later people showed you could build even bigger ones. You could throw in every restricted analytic function. Right, so going forward, we're going to want to talk about complex numbers and functions, and we'll always just identify C with R squared. Complex multiplication and addition are semi-algebraic in the reals under that identification. But of course, you can't have the complex exponential. That can never be definable because then you're going to get the periodic properties, although you can have pieces of it. So we'll see that if you restrict, so e to the z, if you consider the restriction to the whole real line and any fixed horizontal strip, then that will be definable. Because if you write it out in real and imaginary parts, you'll just have restricted sine and cosine and the full real exponential. All right. So what is now the point counting strategy for these problems? How am I going? So I see we're not going to get well, okay. So what's the basic point counting strategy? So we'll look at it first. So point counting for the multiplicative Manin-Mumford conjecture. And I should say that this strategy was proposed by Umberto Zagna to give a new proof of the classical Manin-Mumford conjecture. But how does it work? So here we've got C star to the n and a variety v. And here we've got C to the n, and here is the exponential function, which I'm going to renormalize a little bit just to get rid of the 2 pi i's. So that's a z1, and this is a zn. So we've got this function here. Now, here, of course, so this function is now periodic under z goes to z plus 1. And instead of that picture, this, the strips are now vertical, right? Because I've multiplied by I. So this contains what I'm going to call f to the n, which is, well, for fundamental domain, 0, 1 cross r to the n in here. And now the point is that if x naught in V is torsion of order n, well, the real point is that torsion points here correspond exactly to rational points up here. Rational points map to torsion, and inverse images of torsion are rational. But if V is a torsion point of order n, and Z naught in F is its inverse image, then this is a rational point. And also, it's a rational point of denominator at most n, and less than 1. So it's a rational point whose height is at most n. But this x naught has the coordinates of this x naught are roots of unity, and they have lots of Galois conjugates. So this x naught has, in fact, n to the power 1 minus eta for any positive eta Galois conjugates. And each one of those conjugates has a pre-image in this fundamental domain, which is also rational and of height n. So now we take Z to be the set of Z's in F for which e to the Z is in V, and this is a definable set because it's only using the restricted, the full real exponential, and I mean it's restricted to this set. And what we see is that if x naught contains a rational point of high order, then we're going to get n to a positive power rational points, but we're only allowed n to the epsilon by the counting theorem outside the algebraic part. And so that will prove to us that if V contains a torsion point of large n, then this set Z contains something positive dimensional and semi-algebraic. Now, I'm really running out of time, and I want to at least mention the words Andr Oort. So somehow, let me just say in words what happens now. Once you get something positive dimensional semi-algebraic in here, then because this set is complex algebraic and this map is complex analytic, you get, let me put it over here, because you get that there must be an algebraic subvariety of C to the n whose image is contained in V. And that's a highly restricted situation that you can control by a famous theorem on the transcendence of this function. It can only happen if W is contained in the translate of a rational linear subspace whose image is contained in V, and which then lines up exactly with the exceptional case in the Manin-Mumford conjecture. So that's an issue in functional transcendence, which I like very much, but I can't talk about it here, and actually you prove it well. So I'll talk now about the Andr Oort conjecture, just very briefly. And the simplest, so that in this Zilber-Pink, which is now, well, in this special point problem, you replace this ambient C star to the n by a Shimura variety. And the simplest way to see this is that you replace e to the z by the j function, which maps the upper half plane to the complex numbers and represents the j invariance of elliptic curves as the j function on the lattice. So here the special points are called singular moduli. So let me just say here the basic theorem here is, again, due to Yves André, who proved the analog of Lang's theorem. So let V be a subset of y1 squared. Then if you look for xy's in V, for which both xy are what so-called singular moduli, which means the j invariance of elliptic curves with Cm, as Mark was talking about, then there are only finitely many. Well, unless you're in very specific cases you describe, that V could be a vertical line whose fixed coordinate is special point, or a horizontal line with the same, or a modular curve. And right, so the general case is generalization of that. So let me just put it right here, that you simply replace this picture by taking the upper half plane to the n, mapping to c to the n by the j function on every coordinate. And you have a subvariety here. And the special points here, the pre-images are quadratic points, because it's the quadratic lattices that have the complex multiplication. And so somehow this same basic strategy works. Of course, you have to control this exceptional case. That's what goes by the name of the Ax-Lindemann theorem, and is a theorem in functional transcendence, and tells you that the only times when the image of something algebraic upstairs can be contained in something proper algebraic downstairs is when there's something almost special that intervenes. So I somehow don't have time to really to go through this, but there were somehow several ingredients. So in the general case, let's say you have Shimura variety X is always parameterized by some Hermitian, some open domain in complex numbers, some in C to the n, by some map which is given by automorphic functions under some discrete group acting on this space, which is here SL2Z to the n, right? Which acts here, of course, you have the famous fundamental domain, right, for the j function on the upper half plane. And the j function is definable on that domain, which is a non-trivial statement. And in general, you have a number of ingredients which were set out by Ulmo, that if you have definability of this map on this domain, in your Shimura variety, if you have the Ax-Lindemann statement, which I haven't really specified, if your special points have large Galois orbits, which turned out to be the hardest part of this whole thing, and if the pre-images have controlled height, then this whole strategy works. And that was somehow, these ingredients were put together in the work of a lot of people over quite a few years now. The definability by Petersil and Starchenko, and then Klingler, Ulmo, and Yafayev, and the Ax-Lindemann theorem by various people, including myself with Jacob Zimmermann and Klingler, Ulmo, Yafayev, Dor and Orr on these height bounds in the pre-image, and finally the lower bound on the Galois orbits, which in this basic case is the Brouwer-Siegel theorem. Special points have large Galois orbit because it's the class number of the corresponding order, and that turned out to be really the hardest part of this game, and in a way also another step which but somehow in between there's the case of AG, which is somehow a little bit easier than the general case because you've got the abelian varieties hanging around. But yeah, so all of those ingredients assembled over a number of years, and finally this Galois ingredient, which came also via another counting argument due to Binyamini, Schmidt, and Yafayev, who showed that you can actually reduce the large Galois orbits to a good height estimate via a counting argument on the graph of this uniformization function, because special points give you algebraic points on the graph. And so if you have a counting result which is strong enough, you can use counting to give large Galois orbits if you have a height estimate. And that pushed everything onto the heights and onto Colmet's conjecture and its average version. And, and on the extension of that somehow to that case. Right, so I'll stop there. Thank you.